Welcome back, everybody. The topic this week is to continue and try to wrap up the discussion we had on resampling techniques. This does not sound like the most exciting topic, but it's actually one of the important aspects of a Monte Carlo calculation, which deals essentially with us being able to provide a reliable estimate on the error. Just to repeat a little bit of what we did last week in connection with the introduction to statistical methods and resampling techniques, we scratched the surface of this Bootstrap method. We tried to motivate why we do the resampling. So one of the things which we can do with the statistical tools which we have available is to be able to evaluate the statistical error. Now, one thing which is extremely difficult to evaluate is what we call the systematic error. So the systematic errors are quite many, and one of them deals with the model which we have made. In our case, this is the Hamiltonian, which we have chosen to represent the physical system. And here we have defined a model for which we are not able to evaluate the systematical errors related to the approximation we make to the Hamiltonian. Now, however, since we are doing a Monte Carlo calculation, it means that we have available all possible tools to make a reliable estimate of the statistical errors. So when you present a result of a Monte Carlo evaluation, you have always to provide a standard deviation. This is basically one of the things, if you don't have that, I mean, people will not believe your results. So it doesn't sound, as I said in the beginning, as the most exciting topic, but it's actually a very important aspect of all kinds of theoretical studies where you have the possibility to evaluate the errors. So there are some links here, which we also discussed last time. And if we get time, we are going to discuss one of the final topics, which we will have in project number 1, and that is to define and calculate what's called the one-body densities. So one-body densities are also things which we can evaluate after we have run the large-scale calculations. Bootstrap and blocking, these resampling techniques, are also typical techniques which you would use in a post-analysis of your data. So you would have your Monte Carlo code, which runs and does the heavy-duty calculations, and then writes to file the expected values of the energies. And based on that one, you would then perform a post-analysis, which in our case is the analysis and estimation of the statistical error. There is a very nice both scientific article and a thesis written by Hjorth-Jensen, who was a former Master of Science student at the Computational Physics group. And he actually got the idea for the blocking method and how to prove it in a more rigorous way by following the lectures of this course. So the lectures of this course have tried over the years to follow tightly an article written by 2 Danish physicists, Flyvbjerg and Petersen, and we are going to discuss partly that method today. We need some more background, however, and this background is about quantities like the covariance, how we actually estimate the variance when we have a huge data set, and why we need to move beyond the simplest possible estimation of the variance. Now, as we mentioned last week, this leads to the calculation of something which is called the covariance. The covariance is defined by a double loop over the events which we have. And clearly, if we have billions of Monte Carlo cycles, we would prefer not to have to evaluate a double loop. And this is essentially one of the main motivations for why people have developed these methods like Bootstrap and blocking. And we are just going to look a little bit at the pros and cons, and also at how we can use these methods. And my advice to you is to take the Python codes, which we discussed last week, when we took the top-down approach to things, and then simply use these codes in your post-analysis. There's nothing wrong with that. If you want to write your own Bootstrap or blocking method, you should feel free to do so. But feel free to use the scripts which we put in the Jupyter notebooks last week and discussed last week. So I'm going to switch to the whiteboard. Again, feel free to ask questions if you have questions. And let me just put up the whiteboard here so we can slow down the pace a little bit as well. So the topic which we went through last week was one of the topics was the central limit theorem. And the central limit theorem states that if you have what we called identical and independent, identically distributed and independent stochastic variables. So let me just repeat that one, independent and identically distributed. So that means that all your statistical events follow the same distribution. If that is the case, then what you can show is that in the limit of large samples, large data sets, the final distribution is going to approach a normal distribution with a mean value, which is the same as the mean value of the independent and identically distributed stochastic events. But the variance is going to be given by the variance of each individual event divided by the total number of observables which we have. So the distribution, so in the limit, the central limit theorem, CLM, that states that the final distribution is going to be a normal distribution or Gaussian, an N, which is now given by the mean value of the individual independent and identically distributed variables. And the variance is going to be given by sigma divided by the total amount of experiments which we are running. So it means that we have performed n sets of experiments. Each single experiment has thus a mu, which is given by a p of x. This is a probability for one single set of events. And you can now think of this, if we now have a discrete distribution, this would be represented by the sum over all possible individual experiments. So just think of you running an experiment today, and then you collect n data sets, and this is given by px of I of x of I. Now, normally, what we have is something which we call the sample mean, and the sample mean is not necessarily equal to the exact mean in case we knew the distribution p of x. So the sample mean, which we are confined to live with, is something which we call mu, and it does not need to be equal to mu. So the sample mean is something which we would define as 1 over n. And then since we do not know the distribution, we are simply assuming that all the possible events have the same likelihood, which is 1 divided by n. So this is given by x of I. So in the limit of large numbers of experiments, this should actually approach the true mean. Now, the total distribution, so we would have a set of events now. So suppose now you have, these are the observable, x2 up to xn. So this is one of our experiments. Then each of these experiments has also a variance, sigma squared, which is now given by p of x. And then we would have x minus mu squared of d of x. And in our case, this is going to be equal to the, or not equal. This is the mean, the sample variance. So what is going to come now is a set of manipulations of these quantities, because we are going to rewrite the total variance for many experiments in terms of the so-called sample variance plus the covariance. And the covariance is the quantity which is going to allow us to assess properly the total variance and thereby the standard deviation, which is the square root of the total variance. And then with that, with the covariance, we can then give a reliable estimate on the total error. So we're going to run some manipulations now on the whiteboard where we are simply going to reorganize the definition of the total variance for a given set of experiments. So the sample variance is something which we have defined as 1 over n. And this is now given by the sum over all the data sets which we have for that specific experiments. We have an x of I, but now we have the sample mean, which is not necessarily equal to the true mean value. So this is a quantity which we would like to approximate or get as close as possible to the true variance. This is for one set of experiments. Now, if I repeat these experiments a given number of times, then what the central limit theorem says is that the final distribution should be a normal distribution which has the same mean value as each individual experiment, but it has a variance which is now given by the variance of the single experiment divided by the total number of experiments which we are running. And last week, we looked at a numerical demonstration of that using the Bootstrap method, which we are going to repeat a little bit today as well. Now, what it means is that the total distribution, if we now have this x1s, you can now think of these x1s up to xn as also something which represents a given experiment. But this is normally given now by the product of all the individual probabilities. And since these are independent and identically distributed, it means that all these p's which you see here, these probabilities, they are the same. So each x1, x2, and xn, they have the same mean value. So this is what will happen in case you have independent and identically distributed events. Now, what that means is that an important quantity, which is called a covariance, which measures the degree of correlations between two of these events, xi, xj. And this is the quantity which we are going to focus a little bit on now. And it's actually the quantity we want to evaluate. But this quantity is going to be represented by a double loop over the number of events which we have. And we would like to avoid to evaluate a double loop. So these methods like bootstrapping, blocking, jackknife, and many of these other resampling techniques, they're actually dealing with a way to circumvent the direct calculation of the covariance. So this is actually the task today, to try to present methods which allow us to calculate this quantity in an easier way, and at the same time to calculate it as reliably as we can. So let's take a look at the definition of the covariance. So this is given now by, if we have a given set of events, so we have dx1 up to some dx of n. And this is now multiplied with, so I have an x of I. And since I have assumed now that they are independent and identically distributed, each x has the same mean value. Alternatively, what I would need to plug in would be to plug in a mu of I and a mu of j. But now we are going simply to assume that this quantity here is the same for both events xi and xj. So we're assuming that these are independent and identically distributed. And this is again multiplied now with the probabilities p of x1, p of x2, and up to p of x of n. Now, one of the things which we are going to use is now the fact that these probabilities are normally normalized. So they're normalized to unity equal to 1. And we also have defined mu equal this p of x, d of x multiplied with x. So if I now use these definitions, I can actually rewrite the covariance as follows. So, and the way you read the covariance is actually as a quantity which measures the degree of correlation between two observations, xi and xj. So the covariance then, if I run through the calculation here, now since I only involve xi and xj, I can use the fact that these distributions are normalized. That means that I'm only left with an integral over dx1 and dxi and dxj. And then I have x of I minus mu of x of j minus mu multiplied with p of xi of p of x of j. And you see now that since these are independent and identically distributed variables, it means that this probability here acts only on this part, so the dxi part, and similarly the xj part can then be separated. So what we have then is simply an integral over dxi, and then I have a px of I, and then I have an x of I minus mu, and this is then multiplied with a dxj of xj minus mu over pxj. And you see now that mu is just a constant. That means that the second term which we have here, so this term multiplied with this term, due to the normalization condition, simply gives us mu. And the next quantity gives us the average value, which is again mu. So that means that this is exactly equal to 0. If it's not, if not IID, what we have then is that this covariance, you can easily see that, is going to be given by, so we would have a covariance of xi, xj, is going to be given by the expected value of xi multiplied with xj minus, and then I would have mu of I multiplied with mu of j. And it's actually not so difficult to show that when you run through the calculation here. Now, what we are going to do now is to manipulate the expressions for the variance for a large set of experiments. So if we now look at the sample variance for a given experiment, for a data set, and this is actually the typical situation we have, a data set X, which now contains observable or observations. These are all treated as stochastic variables. In our case, these are the observations which we run when we run the Monte Carlo calculation. So each X would in our case be one value for the expected value for the energy. So we perform one Monte Carlo cycle, we have one expected value for the energy. We then repeat 2, we have a new mean value. We do it many, many times. So we have every time we do it, we keep adding to the mean value of the energy. So in our case, the X's in project number 1, they would correspond to the energies. Or if we are looking at other quantum mechanical observables like the mean squared radius, that could be the mean squared radius for every Monte Carlo cycle. So, but now we're going to keep this in a more general way. So we are going to have the sample variance. No, not that one, but for the data set, let me just wipe this out. So this quantity is now something which I should label as a sigma squared, but I'm going to just take the sigma squared tilde and just write it as sigma squared. And in principle, this is now given by 1 over n, and then I have an I equal 1 up to n, and then I have an x of I minus mu. In principle, I should have this mu bar because this is a sample mean, but I'm going to take away this additional signs, and I'm just going to write, when I write sigma squared, this is now going to represent the sample variance. And I'm going to assume that this is something which we want to have as close as possible to true variance. And the same thing here, the mean which you see here is actually the sample mean, which may not be the same as the exact mean value if you were to know the distribution behind these stochastic variables, x1, x2, up to xn. So this is in principle not the same as the true variance. So the question which we have now is, how do we estimate, based on our calculations, in a reliable way is sigma squared with a given set of data. And this sigma squared defines the standard deviation. The standard deviation and the standard deviation is normally shortened to STD, and that's essentially the square root of sigma squared, which in our case is just sigma. So that means that what we want to present to a potential user of the codes which we have developed, so what we want at the end is a expected value for the observable which we are looking at, which is now going to be given by the mu, which we find the mean value, plus minus this quantity sigma. And that's essentially what we are going to deal with now. And these resampling techniques, the way you should view them, they are techniques which allow you to estimate the standard deviation in a hopefully most reliable way. So let's go through the some of the basic elements of the calculation of the sample variance. So let's now set up the type of machinery which we need to run this analysis here. So what's going to come now is a set of manipulations. So what we are assuming now is that we assume now that we perform a set of experiments. And this is pretty close to the way we are going to parallelize. So we assume we have now M experiments. So when I say experiments, it could be a real experiment, but when we think of the Monte Carlo calculations, you have to view them as numerical experiments. We have M experiments, and each experiment and each has N observations. Now you can view this in many different ways now. So one way to view it is that you run your program in parallel and you have M different processes. And in each process, you compute N Monte Carlo calculations. So that means that you have M different processes. And in each process, you perform now N calculations of your energy. So that's one way to view the kind of data set which you can produce. Alternatively, you could now think of you running a Monte Carlo calculation with N observations or N calculations of the expected value. And then you would do something like M bootstraps. So where you take that data set you have and you reshuffle these numbers in order to produce artificially a new experiment. So you see now there are different ways by which you can view this statement here in actual experimentations. The standard situation for an experimentalist is that they would run a given experiment, and if they are allowed to rerun it, which often is unlikely because an experiment can be pretty expensive, then an experimentalist, in order to evaluate the standard deviation in the most reliable way, would typically perform a post-analysis using a resampling technique like Bootstrap. Now, one of the reasons why we are not going to use the Bootstrap for the type of Monte Carlo calculations we are doing is that we are going to produce billions of observations. And then the Bootstrap becomes actually inefficient from a computational point of view. It's actually going to spend, we are going to spend more CPU cycles on the Bootstrap method when we go beyond something like 1 million Monte Carlo cycles. So the Bootstrap is a technique which is often used on, let's say, up to 100,000 observations. And these are the observations of the type N here. And then you would resample your data set. But when you move beyond that, the method becomes very CPU inefficient. And that's where the blocking method has become one of the standard methods which is used to evaluate the variance in the most reliable way. So there's always a kind of trade-off. If you have less than 100,000 data points, most people tend to use the Bootstrap method to evaluate the expected variance. If you go beyond that, then the blocking method tends to be the favored method. So in our case, I would normally recommend that you run the blocking method, but you should feel free to use both methods and compare them. They're going to give slightly different results, but only slightly different results. And the reason for that is that most of the implementations of the Bootstrap method, they assume that you're dealing with independent and identically distributed variables. The blocking method does, in principle, not take that into account. So there are lots of these kind of statistical considerations which we need to think of. So let's now think of each experiment here, and let's introduce a notation which we need. So what we're going to say now is that each experiment has its own mean value and its own variance. And let's call each of these experiments, label this as alpha. So it means that this experiment has a mean value, mu of alpha, which is simply 1 divided by n. And then I have a sum of k equal 1 up to n. And then I have an observation here, x alpha of k. So this is experiment alpha. So you could think of you running a Monte Carlo calculation on one specific core, and that would be core alpha. And you run this n times. Then it has also its own variance. So it means that there is a sample variance in this case. It has a variance, which we are going to call a sigma squared alpha, which is simply 1 over n. This is just a straightforwardly stating the definitions of these quantities. So it has an observation x alpha k minus mu alpha squared. So there's nothing exciting about that. Then we are going to repeat this m times. So the way we repeat it is obviously something which we define. So one way to repeat it is to perform a bootstrap of the data set. Or if you're allowed to do so, you can rerun the experiment, a real experiment. Or if you're running things in parallel, this could just be the output from each specific process. So if you're running 1,000 processes, you would have this 1,000 m equal to 1,000 processes. So you repeat m times, and that means that you are going to have a mean value, mu of m, which is going to be given by 1 over m, and then I have an alpha equal to 1 up to m, and this is given by this mu of alpha, and this is finally given by m of n, and it has a sum over alpha and k, and then we have the final observation, which is our alpha k here. This is the way you would actually calculate the mean value from a parallel job of Monte Carlo evaluations. You would simply collect all your data points and calculate the mean value based on the output from m parallel processes. And one thing you should keep in mind when you run this in parallel, which will be the discussion which we are going to have next week, when you run this in parallel, you should start each process with a different seed. So it's pretty common to actually start the processes using the clock, so that each specific process starts with its own set of initial random numbers, and they will produce a different chain of random numbers, so that each experiment has a slightly different output. Then, with this quantity here, we can also define the total variance. Actually, I promise you that this is not so exciting, but we need this expression just to manipulate and find a more compact expression for the variance in terms of the variance of a single experiment and the covariance. So this is then defined by 1 over m. And we have alpha equal to 1 up to m here. And we have a mu of alpha minus mu of m. And this is something which we then can rewrite if we now look back and look at mu alpha minus mu of m. This is simply going to be given by 1 over m and n. And then we simply set up the sum here, which we have a sum over alpha up to m and n. And then we have x alpha k minus mu of m. So remember now that mu of m is just a constant. So when I sum over this quantity here, I can just put it outside, which means that this sums up to m and n, and you divide by m and n. So then I'm just back with mu of mn here. And the quantity which you see first here is actually the way we define this mu of alpha. Sorry, this mu of alpha should actually be, that was not correct here, because the mu of alpha is just given by one of these experiments. So I should not have a sum here. I should just have a sum over k here. Okay, so we can plug that back into the equation for the total variance. So if I do that, then I can rewrite the total variance in terms of these quantities. And it's pretty easy to show that this becomes equal to, if we now look at what we have. So let me just do the calculations here and the intermediate steps. So we have a sum over alpha 1 up to m. And when I square it, I get a mu alpha squared minus mu alpha mu of m minus mu alpha mu of m. I'm just squaring the definition for the variance. So when you then look at these terms here, so this is just a constant. And then I have this term here, which then defines mu of m. So I get minus 2 mu of m plus mu of m squared, minus 2 mu of m squared plus 2 mu of m. So that is going to give me something which is equal to 1 over m. And then I have alpha equal to 1 up to m. And I have my mu alpha squared minus, and then I have my mu m squared. Then I can plug back the expressions for mu of alpha. So mu of alpha here is simply, if I go back now and look at the definition for mu of alpha, what I'm going to plug in is simply this term here. And since this is squared, I have to plug in two double sums. So this means that what I'm having now is something which is going to be given by 1 over m. It's going to have a loop alpha equal to 1 of m. And then I'm going to have a 1 over n, k equal to 1, up to n of x alpha k. And then I'm going to have a 1 over n, and I have an L equal 1 up to n of x alpha L, like this, minus mu of m squared. Now I can reshuffle this, and you would see then that this becomes equal to 1 over m of n, and then I have a sum over alpha. I have a double loop over k and l, and that runs up to n. This runs up to m. These start with 1, so this is a free sum, and we are going to reshuffle that free sum as well. But we can rewrite this as an x alpha k minus mu of n multiplied with x alpha L minus mu of m. The next thing I do now is I pick the diagonal element, and that means that k is equal to L. So I can rewrite that in terms of 1 over m n squared. And then I have a sum, so I'm just picking the diagonal element, and I'm going to write this as alpha k. So I'm going to have an x alpha k minus mu of m squared. But then I can rewrite the non-diagonal terms, since the non-diagonal terms is now a loop which runs freely. This quantity is symmetric. which means that I don't need to sum over all K's and L's, but where K and L are different because I picked out the diagonal elements. So I can rewrite this one as plus. And since this is a symmetric quantity, then I get a factor of 2. And this is divided by m of n squared. And then I have a sum over alpha equal to 1 up to m. And then I have a sum over k less than L up to n. And then I have my x alpha k minus mu of m. And this is multiplied with an x alpha of L minus mu of m. So this sounds very exciting, actually. So the other thing I can do now is to define the sample variance of all mn experiments. So if I take the sample variance of all mn experiments, assuming now that if these are actually identical and independent identically distributed events, then I should not have a second term which measures the correlations between the events. But the sample variance is something which I'm going to call sigma squared here. And that's given by 1 over m of n. And it has a sum over alpha and k. So these are just the diagonal elements of x alpha k minus mu of m squared. So you see now that what I can do is that I can rewrite with this definition, I can rewrite my total variance in terms of the variance of the specific experiments. So I can rewrite the sigma squared of m in terms of this sigma squared divided by n here, plus a term which is actually a quantity which defines the covariance. So this quantity which we have here is another way of writing the covariance. I'm just simply going to call this the covariance cov here. So what we want to do now, we want to evaluate, we want this sigma m squared without having to evaluate the double sum, which you see here. So the quantity which is going to be time consuming for us is actually this quantity here. So I want to avoid to evaluate this cumbersome double sum. So the whole thing with a method like blocking, but also bootstrapping, is a way to circumvent the direct calculation of this quantity here. So without having to evaluate, now, there are many interesting aspects here, which we are not going to touch upon. So in statistical physics and also in the statistical data analysis, but in particular in statistical physics, we are also interested in finding out the degree of correlations between the observations which we have. For those of you who are more interested in statistical physics and simulations of models like, let's say, the Ising model or Potts model, the classical models which simulate phase transitions, actually this covariance becomes a very, very important quantity. And if you have a typical phase transition of what we normally call the second order type, where your heat capacity would peak at a given temperature, that means that you're actually moving into a different thermodynamical phase, then typically this covariance would actually explode due to correlations in the system, so that you would have an infinite so-called correlation length in the system. And that will have pretty important consequences for quantities like the covariance. It's also a way to measure the correlations between, for instance, random numbers. And if these random numbers are really independent and identically distributed, this covariance should actually be equal to 0. So the way we are going to look at the discussion now is more as a way to circumvent the calculation of the covariance. But the covariance itself is a very important quantity, because in many applications of these methods, we do not have independent and identically distributed stochastic events. So that means that this covariance is normally non-zero. Now, the covariance, as you can also see from the equation here, the equation which we have here, this quantity here is a positive quantity. And it means that this quantity here is larger or equal to 0. That means that if I omit the covariance, I may get a standard deviation which is way too optimistic. So the covariance is an important way to correct the standard deviation and give a reliable estimate to the standard deviations. So what we are going to do now is to remind ourselves quickly about some of the resampling techniques which we discussed. So let's quickly remind ourselves about the Bootstrap method. So the Bootstrap method is a way to generate m such experiments, but just reusing the same data set. And this is often a technique which is used when you have experiments which may be difficult and expensive to run. So if some of you is going to deal with a lattice quantum chromodynamics, which is a quantum field theory in the lattice for the strong force, then to run and obtain something like 1,000 to 10,000 observations is something which can take months on a high performance computing facility. So if you look at the Bootstrap, so we have now X, an observation here, set of observations which contains X1, X2, up to some Xn. And then we are going to perform M bootstraps. And this is the way we are going to generate the data sets which you could have thought of generating by an experiment. So the first step now is to compute the standard deviation or the variance, compute nu and sigma squared for the data set which you have. The next step is to reshuffle the data set, full data randomly. Randomly by selecting. So you would select n observations, n points or observables with a replacement. So you would actually place them back in the data set and then perform a new random selection with a replacement. So that means that you could now generate a new data set, which we are going to call X prime. And that could be something which now looks like X3. There could be an X5. Now you could pick X5 again. And this could go now up to some X, let's say n minus 50, just to give you an example. But the total length is still n. So I have n observations. But I have simply picked randomly with replacement a given set of observations, or in our case, n observations from the same data sets. Then what I will do now is to compute sigma squared prime and mu prime. And next, I will simply repeat these steps, repeat m times. So you could now think of you artificially generating m new experiments. Then the final step is actually to find or compute, for instance, the standard deviation, which is now going to be given by sigma squared, which is 1 over m. And we would then have a sum over all the different experiments which you made, or reshuffles which you made. And we are just going to put this as a sigma I squared. So this becomes time consuming when m is large. So this is time consuming when n and m are large. And that leads us to the next method, which is widely used when n is large. That leads us to the blocking method, which we are going to outline in the next lecture. And this typically is used when n is larger than something like 10 to the 5 to 10 to the 6. Because if we were to do blocking, then this would quickly become pretty time consuming. And Bootstrap. If you're doing blocking, then it's actually much more efficient than doing Bootstrap for large data sets. So there's a kind of balance of the regions of applicability of these different methods. Now I see we have hit the hour. So what we're going to do now is just to rewrite a little bit the equations which we had up here for the total variance. And we are going to rewrite it so that we can adapt that one to the derivation of the blocking algorithm. So what we're going to do now is to bring up the basic elements of the blocking method so that you can implement this and understand how actually it is going to function. So to quickly remind ourselves of what we did before the break. So we have this sample mean. Which we defined as a mu of alpha. So this is one specific experiment, and we just simply call this mu of 1 over n. And this is gives a sum of k equal to 1 up to n. And then we had the specific observation of alpha of k. Then we repeated this mu times, n times. So we ended up with a total mean, which is 1 over m of n. And we have a sum over alpha equal 1 up to m. And we had a sum of k equal 1 up to n here. And we have an x alpha of k. Similarly, what we did was to define the total variance in terms of these individual observations. So what we had then was a sigma of m squared, which is equal to the sigma squared, which was the so-called sample variance of all the observations which we had, plus 2 over mn squared. And then we have a sum over alpha equal to 1 of m. And then we had this double sum over k less than L, and this runs up to n. And then we had an x alpha k minus mu. And in principle, this could be different, but we actually put it equal to mu of n. And then we had x alpha minus mu of n. And this sigma squared, just to complete what we did before the break, is now the variance of all the single observations here. Alpha, and then a sum over k, and this is given by x alpha k minus mu of n. So all this analysis rotates around us being able to calculate this quantity, this so-called covariance quantity or this correlated quantity, without having to evaluate a double sum. Now, this term, the last one, is the one which arises from the diagonal term, which means that we put k equal to L. We're going to introduce a shorthand. And notation for a quantity which I'm going to call fd. So this quantity is called f of d, and that is given by 1 divided by n of m, and it contains a sum over alpha equal 1 up to m. So I'm just going to put in a new quantity, k equal to 1, and this goes up to n minus d, and it's going to be given by x alpha k minus mu of m multiplied with x alpha of k plus this quantity d minus mu of m. So what I'm going to do now is just to rewrite this covariance term in terms of this quantity f of d. And this d here is simply the absolute distance between k and L. So instead of having an explicit sum over L, I'm going to replace that with a summation over this quantity d. So this quantity d is also an interesting quantity because we use that one to define something which is called the autocorrelation function. And in statistical physics, but also in statistical analysis, the autocorrelation function is very important because it gives you a measure of how correlated your observables are as a function of the distance between an observation. So the autocorrelation function is something which is normally defined as this kappa of d, and this is given by fd divided by sigma squared. And sigma squared is this sample variance over all the observations which we have. Now, if you now look at the fd of f of 0, so this is the case with d equal to 0. If you now look into the expression, what you will see is that this is actually equal to 1 over n, and it has a sum of alpha equal to 1 up to n, and it has a sum which goes from k equal 1 up to n, and it's simply x alpha k minus mu of n squared. And this is nothing but this sample variance which we defined, not the total variance, but the sample variance. So that means that this correlation function k0 is given by sigma squared divided by sigma squared. So it has one point which has to be exactly equal to 1. So when you're calculating this correlation function, and if you don't get 1 when you have d equal to 0, then you've probably done something wrong. And if you make a plot of this function, this is a function which has a behavior which looks like this as a function of d. So the more far away the observations are, the smaller we are hoping that this autocorrelation function should be. So when I take 0 here, so the first, if I take d equal to 0, then I should have 1. So I'm plotting this quantity kd. And then the next observation, and the next, and the next, we are obviously hoping that these are numbers which will be as close to 0 as possible. So when these numbers are 0, suppose they look like this now, we have these are the observations. So ideally, we would like this to be as close to 0 as possible. And the larger the value of d, we would then think that the numbers which we observe have basically no correlation. Now, the reason why I'm mentioning this is that this is something which is important for the blocking method, because the blocking method tries to relate observations with a given distance between each observation. So the smaller this correlation function, the more certain we are that these specific events, which are separated by a specific distance, are less correlated. Now, when I use this function f of d, what happens then is that I can actually rewrite this sigma m squared in terms of this sigma squared divided by n plus 2 divided by n. And then I'm going to have a sum from d equal to 1. And this runs up to n minus 1 of this function f of d. And the, sorry, there should be not exactly that one. I just missed one term here. So this is, this is going to run from d equal 1 up to n minus 1 of f of d. So I can actually rewrite my total variance in terms of this correlation function. And if I now bake in this autocorrelation function, which I defined previously, so I can rewrite this one as a sigma squared divided by n. And I have 1 plus 2 times d up 1 up to n minus 1 of this correlation function k of d. And ideally, we would obviously like to be able to have a estimation of these terms kd without having to calculate the double loop, as we announced previously. So this, what you see here is the basic mathematics which is needed in order to understand the blocking method here. So let's now take a look at what Flyvbjerg and Petersen actually introduced. So let's look at the blocking algorithm or the blocking method. And let me point you to the paper, the original paper by Flyvbjerg and Petersen. So this is a paper which is in a Journal of Chemical Physics, 91, that's volume 91, 461 from 1989. In their paper, what they did was to define the following quantities. So when you're reading the paper and you want to link that with the quantity which we have here, so this is the basic quantity which they want to evaluate with the blocking method. So let me try to explain to you the way this method functions. In order to do that, and if you're going to read the paper by Flyvbjerg and Petersen, I want to bring up their definitions so that you can see the link between their definitions and what I defined here. So this is a kind of expression, this one, which you will encounter in most textbooks on Monte Carlo calculations, and also calculations applied to statistical physics, statistical mechanics, applications of Monte Carlo calculations. So if you're simulating, for instance, the Ising model, this is a typical quantity which you would see in the evaluation of the standard deviation. So Flyvbjerg and Petersen, they defined mu as we did. So it's a 1 over n. This is the specific set of data which we have. So in this case now, n runs over all the data sets. So in our case, this could now represent the collection of all the experiments which we have done. So that means all the single experiments m, which each contain n observations. So n now is the total data set which you have. And then they define a sigma, which they call a mu, which is now simply the observation or the mean value of x squared minus the, actually this is the mean value squared, so let me just write it like this, or mu squared. Then if you move on now, suppose that we take this m, which we had previously, and put that one equal to 1. So that means that our sigma squared of m is equal to sigma 1 squared, and this is equal to sigma squared divided by n plus 2 over n squared. And then we have this quantity which we called k less than L. So this is the starting point in the analysis of Flyvbjerg and Petersen. And we replace this with a mu value. So x of L minus mu. So I'm simply now assuming that my total data set is n, and I put this n equal to 1. And this is what they, in their article, define as sigma squared of mu. Then they define a new quantity, which is actually given by the covariance. So this is given by the expected value of xi of xj minus the expected value of mu squared. And they actually label this as a gamma of t, where t now is the distance between an observation I and an observation j. So if you go back to what we did when we defined this quantity f of d, this is essentially the same mathematical quantity which we had in here. So if you look back at that expression, we're actually looking at this one, and where we define d as a distance between two observations. So it's almost the same quantity. It's not exactly the same. So with that definition, you can then show that your variance can be written as 1 over n squared. And this contains now a sum over ij of this gamma ij. So if you take the diagonal component, you're going to get back this component which we have here. And then the non-diagonal one will be represented by this quantity. So this, when you go into the article by Flyvbjerg and Petersen, this is nothing but just another way of rewriting what we defined in the previous lecture and in the beginning of this lecture. Then you can rewrite this in terms of 1 over n, and it contains a gamma 0. And this gamma 0 is the same as this quantity which we have up here. So note now that they use a definition with sigma squared of mu, and that's not the same as this sigma squared here. So this quantity which you see here is going to be the same as the one which we call sigma squared. And then you can then show that this can be rewritten in a compact form as a sum over t equal 1 up to n minus 1. And then as a 1 minus t divided by n multiplied with this gamma of t. So this is essentially what we wrote before. And the algorithm here goes as follows. So let's look at the algorithm. So what we want is to evaluate this quantity here in a cheap way. So let's take a closer look at the algorithm. So we have the data. We want to transform the data set into blocks where we half the data in each iteration. Transform. So we transform the data. So we have a data set which is X. This is our total data set, X1, X2, up to Xn. This is transformed into half as large a data. So we're making blocks. So now we are making blocks which obviously has only half the data, but it contains information about all the data which we had. And what we are doing now is to rewrite this in terms of a new data set, which contains an x1 prime, an x2 prime, and this goes up to an x of n prime. And where this n prime now is simply half of the data set which we had. This means that we need to redefine the x's. So this x of I prime is equal to 1/2. And then we have x2 of I minus 1 plus x2 of I. So what we're doing now is, instead of like in Bootstrap, where we would pick randomly the data set, we are now regrouping the data by taking neighboring data points. And that defines a new variable. So the information is not lost. And one of the things you will observe here is that mu prime, when we calculate the mean value, that should be just the same as the previous one. So this is unchanged. Similarly, it's pretty easy also to show that this sigma of mu prime is the same as the sigma of mu. So that means that the total variance is not changed. The benefit of doing it like this is that we are going to be able to evaluate these variances in an iterative way, where we split the data set into blocks. And after having done this splitting a certain amount of times, what we are going to see is that this term here stabilizes around a specific value. And when it stabilizes around a specific value, and you can show mathematically, and this is what Marius Johnson did in his master thesis, was to show that this actually reaches a saturation, this value here, by repeated divisions by 2 of the data set and making the kind of transformation which you see here. So suppose now, as an example, take a data set. Let's suppose our data contains 6 points. So we have an x1, x2, x3, x4, x5, and x6. Now, we are going to make life very simple. So this could be the outcome of rolling a die. So we have a 1, 2, 3, 4, 5, 6. And you see now that the mean value is simply 1 divided by 6 of xi. And this is the same as 7/2. And this is going to be the same if you now plug in mu, which is now going to be 1 divided by 3. And with the I equal 1 up to 3. So here I equal 1 up to 6. And then you're going to have this x of I primed. So if you go back and look at the expression for this x of I primed here, then when you're plugging it in, you will see you get a factor of 1/2. Multiply that with the 1/3, you get back the 1/6. And when you plug in these expressions, you're actually back to the same calculation of the mean. So the mean is unchanged. The mean should not change when we make this type of transformations because the data set is not changed. Then you can calculate the mean value. So just to give an example, so we calculate this with this mean value here. So that would be 1/6 and I equal 1 up to 6. And then you have an x of I squared minus mu squared. And that's supposed to be 8 divided by 3 if I've done the math correctly. Then I can do the same with a transformed data set, mu prime. And this is going to be equal 1/3. And then I have a sum from I equal 1 up to 3. And then I have an x2 of I plus 1, sorry, minus 1. Plus x2 of I divided by 2 here. This is squared. And minus mu prime squared. And when I plug in the numbers here, what I'm going to get is 1 divided by 3. And I have x1 plus x2 squared divided by 4 plus x3 plus x4 squared divided by 4. And then I get an x5 plus x6 here divided by 2 and divided by 4. And minus mu squared prime. And this is also going to be 8 divided by 3 if I've done the calculations correctly. So this is simply just to show you that the variance is unchanged, the total variance, as it should. So it means that we are not losing any information when we run these calculations here. Now, the thing which also happens, if we now look at these variables which we defined, so we had an x of I prime. In x of I, we end up with a gamma ij, which we then relabel as a gamma of t. Here we get a gamma ij prime, so this is changed now. And this is equal to gamma of t prime. You can show, and I'm just going to give you the final expressions here, is that gamma of t prime is going to be equal to 1/2 of gamma 0 squared. And this is our original result, sigma squared, without any correlations. And this is has an additional term of gamma 1/2 of 1. And it's not gamma squared, sorry. That should not be there. And this is the result we would get when t is equal to 0. So it means now that if I look at my first data set where I split the data into 2, then my total variance should now contain the original result plus this term here, which is now an estimate. This is going to give us an estimate of this term which you see here, this specific term here. So it's when I start with t equals 0, I'm going to get one specific estimate, and when t is larger than 0, then I'm going to get a slightly modified expression, which is gamma of 2 times t minus 1 plus, I'm not going to go through the derivations of all these quantities, but you can try it yourself if you want to. 1 divided by 4 of gamma of 2t plus 1. So t larger than 0. So it means that our gamma 0 prime is now going to be equal to 1/2 of gamma 0 plus 1/2 times gamma 1. This means now that what happens if we now go back to the expression which we had up here, it means that every time now I split my data set into 2 halves. So in the first operation, when I split it just by 2, I have the full data set and then I split that by 2. What happens then is that my gamma 0 is changing, and my gamma 0 is now changing to, so when I split it in half once, so I get a gamma 0 prime, which is easy to evaluate because it's simply given by gamma 0, the original result, plus 1/2 of gamma 1. And these are quantities which I can easily evaluate. So I know what this gamma 1 is, I can calculate it, and then I would simply just proceed with these type of calculations till what happens. So I would then keep halving. So I would continue splitting the data in halves. Let me just in halves. Which means that what we're going to have now is something like this, till this gamma of t prime reaches a constant value, so that it converges towards a constant value after t operations here, or t blocks. So what you would see then is something like this. If we now take and write this as a function of the number of blocks, which we have done. So we would have the first block 0. So that's the full data set. And that corresponds in our case to a data set, which now is simply the raw data which we have of x of n. In that case, we are going to compute gamma 0. So in this case, we have gamma 0, which is equal to sigma squared divided by n. Then I take the next block. So I have a new operation. So I have now a new data set, which is x1 prime, x2 prime, up to xn prime. And now in this case, n prime is equal to 1/2 divided by n. And then I would continue to the next one, which then would contain an x1 prime, double prime, x2 double prime, up to an xn double prime here. And where now the n double prime is actually equal to 1/2 of n prime. And it would continue like this till we find a kind of saturation. So what I would get now in the next one here, I may get now a gamma 0 prime. And this gamma 0 prime is 1/2 of the previous value, gamma 0, plus 1/2 of gamma 1. And this is normally a value which is larger. This gamma 1 is larger than 0 because the covariance term is larger than 0. And this will now continue like this. And when I now reach a kind of plateau here, it means I have reached a size of the blocks where essentially the covariance term doesn't change. So it means that I have reached a situation where you can now think of, you have a distance between your variables, which can be considered as an ideal distance where you can think of the different variables as being independent and identically distributed. So the blocking method, the way it was implemented by Flyberg and Petersen in the original paper, was a method where you would simply now calculate the total variance as a function of the number of blocks. And when it reached a plateau, then you would say that I'm satisfied and I have reached the optimal value for my total variance. So this is the optimal total variance. And the size of the blocks then tell you something, or how many times you have to split it. It tells you something about what is the distance between a measurement before you can start thinking of treating these measurements as independent and identically distributed. Because when this flattens out, it means that when you keep changing this from iteration to iteration, or from block to block, as we might call it here, it means that this term, which arises from the correction, and if we go back to the expression for the covariance, which we put up, it means that the term which we put up here, this term here, reaches a saturation. And when this has reached a saturation, we are simply saying that the variance is going to be dominated by the primed gamma zeros. And the second term produces a result which is close to zero. So it's a way to figure out what is the kind of distance between measurements, so that you can claim that these measurements are to be considered as independent and identically distributed. So this is the essence of the blocking method. And it is a cheap way to evaluate the standard deviation when you have large data set. So the method is normally applied to n data sets when n is typically from 10 to the 5 or larger. Note also that since we are splitting everything in blocks by dividing by 2 all the time, it is then convenient to have n in powers of 2. So to have n which is proportional to 2 to some quantity which we might call for k, and where k could typically be something like 20 or larger. So if you're using the blocking method, since you're dividing by 2 all the time, it is actually convenient to split to initialize your Monte Carlo cycles, the number of Monte Carlo cycles with base 2 to the power of something. Okay, this was about the kind of resampling techniques which we would end up using. And I would recommend that you use this as a kind of post-analysis of your data, which means that you would typically run your Monte Carlo calculation, produce an output, and with that output, you would then perform a post-analysis with resampling methods like either the Bootstrap, depending on how much data you have, or the blocking method. And feel free to use the functions which we provide you with. So any questions so far? Things which are unclear? Because if not, I'm going to say something about the one-body density. So this is a final topic, which is, except for parallelization, which we haven't covered yet. So if you look at these one-body densities, these are extremely important ways to display our results. So the one-body density is a quantity which is now defined. If you think of one of the particles, you can pick any one because these are independent particles and indistinguishable. So you could now think of particle 1. And formally, this is now given by the integral of d tau, or let's write this as an r instead of tau. Now let me just do that. Let me write it in a different way. So this is given by an integral over all the particles, except for the particle you're looking at, d3 up to dr of n. So these are the number of particles you have, multiplied with a wave function squared. So you would then have a final trial wave function with the optimal parameters. You would have this as a function of R1, of R2, up to Rn, and as a function of the optimal parameters, which you have found from your Monte Carlo calculation here. So this should be squared here. So this is the formal definition of the one body density. So if you have a non-interacting case, and with the harmonic oscillator, this is pretty easy to calculate. You can choose whether you want to normalize this quantity or not. The quantity you would plug in here is now something which depends on the results you get after you've run your Monte Carlo machinery and you found the optimal parameters. So you need actually to have the optimal alpha parameters. When you have found the optimal alpha parameters, then you can calculate the one body density. So if you look at the non-interacting case, and let's now rewrite this R1. If we now are in 2 dimensions, we would plot it as a function of R1, which is then equal to x1 squared plus y1 squared. If you're in 3 dimensions, you need to add c squared. So it's convenient now, since we are going to look at a system which is going to be in the lowest single particle state. So this is going to be a system which has a wave function which is isotropic in space, which means that it has the same angular dependence in 2 dimensions. This gives us just a normalization factor of 1 over 2 pi for the angles. And then we can simply plot this as a function of the relative distance, or if we have 2 particles, we want a 2-body correlation. If you have a 1 particle, it will simply be as a function of the absolute value of its radius when you made a transformation to spherical coordinates or polar coordinates. So it's convenient to plot it as a function of r. So what you would see then, or what you would need to do, is to make a table of x1 and y1 values and compute this quantity rho as a function of x1 and y1. So you would fix x1 and y1, so you can make a table here. So you could think of you having 10 points for x and 10 points for y. They could be equal, doesn't matter. So you could have a quadratic grid for x1 and y1. And then when you have these x1s and y1, then that would clearly give you rho of r1, where you're plotting the absolute value of r1. You're not calculating the vector r1, but you're simply calculating the absolute value. And remember now that we are assuming that this is a wave function for the single particle degrees of freedom, which is isotropic in the angles. So it's isotropic in space, which means that it has the same value as a function of the angle. So what you will see then when you plot this for the non-interacting case, so if we take this case first, you could see something like this. So I'm just making a sketch here. So this will be as a function of R1, and this will be your rho of R1. So what that expresses is the likelihood of finding a particle with a radius, or we might call it the absolute value of the distance from an origin for particle 1. But since we are dealing, these are independent and, they are indistinguishable particles. This applies to particle 2, particle 3, and so on. Now, the thing which is interesting now, if we add interactions, this one body density reveals some very interesting features. That if I add interactions, so we can now have a repulsive interaction, or we can have an attractive interaction. So let me just change that one. Let's change colors a little bit there. So I can have a repulsive interaction, so the particles repel each other, or I can have now an attractive interaction. So let's just write that one. So let me see what your intuition says here when we're now going to make a plot of these one body densities. So I'm going to make a plot again. So the as a function of R1. The first function here is the case with no interaction. It doesn't need to look like this. So this depends a little bit on how I have scaled my problem. So if you take the full wave function, your full wave function is going to look more something like this. So you can scale the interaction in 2 different ways. Now we have no interaction. Now, if I plot this for a repulsive potential, so let me try to find out, to trigger your intuition here. So if you look at this, this is a case with no interaction. If you add a repulsive interaction, would this particle, how would this one body density look like? Would it be shifted towards larger values of R1, or would it be pulled in towards smaller values of R1? What is your feeling? You can answer in the chat if you want to. So if I have repulsion, should it be pushed out or pulled in? So you can unmute yourself, or you can answer in the chat if you want to.
Pushed out.
That's pushed out. Excellent. So what you would see then, so this is actually a quantity which you would see something which would be something like this if we have repulsion. And then if we have attraction, then it will be pulled in. So we could then see something like this. So this is just a little bit exaggerated here. Now, why is this an interesting property? So the one body density is interesting because you can relate that to experimental information. So the one body density is a quantity which would enter the charge distribution of particles in a medium. So if you can measure this quantity experimentally, and you then run a calculation with no interaction, and you compare that with the experimental results from a charge distribution, if you're dealing with charged particles, so this is something you can actually extract from experiment, then you could say something about whether the interaction has to be repulsive or not, depending on you thinking of the non-interacting case as the ideal simulation of a system. So it's a very interesting thing to actually look at. So if you start with a non-interacting case and you believe that that describes the system when no interaction is on, and then you're able to compare that with experiment, you can say something of whether the interaction is going to be attractive or repulsive. So this is one of the kind of measures also of the strength of the interaction. So if your interaction is very strong and it's strongly repulsive, what you will see then is a larger difference between the no interaction case and interacting case. So it serves also as a kind of measure of the strength for the interaction. So if you see large differences, that clearly indicates that the potential which is acting between 2 particles or more particles is an interaction which can be strongly repulsive or strongly attractive. So it's a way to convey information about the physics of the systems in a very simple way by looking at the distribution of of particles. So the one body density simply tells you what is the likelihood of finding that specific particle at a specific distance. And this is obviously influenced by where the other particles are. So if you have an interaction which is then repulsive, then that means that this particle will actually be pushed away from the origin. To calculate it, what you need to do is simply to make a table, and if you're in 2 dimensions of x and y, and then simply evaluate that integral. So you would evaluate that integral by Monte Carlo integration in the same way as you've been evaluating the energy. So to calculate the integral which you see here, this is just another Monte Carlo calculation. And many people, when you have actually set up the calculation for the optimal parameters from which you start your large scale Monte Carlo calculation, what you would do then is also to evaluate that integral which you see here while you calculate the energy. So that's one possibility. And then you would simply produce a table with x1s and y1s, or a table which just has x1 squared plus y1 squared, and that gives you R1. And then when you have that, you have this density as a function of R1, you can make the plot and then analyze the results in terms of non-interacting and interacting wave functions. The non-interacting case, since that is a harmonic oscillator, is very easy to calculate because that's just an integral of Gaussians. That's just an integral which contains e to the minus R1 squared, R2 squared, and so forth. And that's something which we can calculate analytically without any problems. Whereas for the interacting case, we need to calculate it numerically. And it's a useful test when you calculate the one body density and you start with a non-interacting case to just see that your code gives the same result as you would expect from an analytical calculation with a harmonic oscillator wave function. Any questions to what we have been discussing today? So I'm going to stop the recording.